Hello class, so let's try to solve this problem on the ideal Otto cycle or air standard Otto cycle. Okay, the given is that the cycle has a compression ratio of 8, and at the beginning of the compression process, air is at 100 kilopascals and 17 degrees Celsius. And then 800 kilojoules per kilogram of heat is transferred to the air at the constant volume heat addition process. We are required to determine the maximum temperature and pressure that occurs during the cycle, and also the network output and the thermal efficiency. So in solving problems dealing with the air standard power cycles, even the Brayton cycle and the jet and rocket engine cycle, it's better for us to know the s- um, the process, okay, at each step of the cycle. So if whether it's isentropic, isochoric, isobaric, so it's very important for us to memorize, okay, or be familiar with the steps kasi that would be the basis on what equation um, is applicable or what equation can we use. Okay, first let's write the given. Okay, given. So we're given uh, P1, so start of the compression, diba? Start of the compression. So P1 equal to 100 kilopascals. Okay, and then T1 equal to 17 degrees Celsius. We are also given a compression ratio. So what is the compression ratio? It's the ratio of the volume, the high volume and over the low volume. So let's write it as V1 over V2 equal to 8. Okay, ano pa yung given? Um, Q in, okay, Q in this value right here. Q in is, or Q at 2 to 3, okay, is equal to 800 kilojoules per kilogram. Okay, and then our assumptions is that this is an air standard or an ideal Otto cycle, and air is an ideal gas. So assumption, air, the ideal Otto cycle, air is an ideal gas, Ig. If, and also um the Cp and Cv or specific heat are not a function of temperature. And we can take Cp is just equal to 7 halves R. So this is for air. 7 halves R. Cv is 5 halves R. Okay. And gamma is ratio of Cp over Cv is 1.4. Okay. Then we write the required. So the required are the Tmax, maximum temperature of the cycle, Pmax. So by the way, before that, um, based on the diagram, where does P max occur? Diba it's at T3. Okay, right here. And then, or in the PV diagram, it's here. And P max, where does it occur? Diba it's P3. P3. So, we need to know T3 and P3. For letter B, the network. Okay, so work net. And letter C, the thermal efficiency. The efficiency, since uh, we assume that this is an ideal cycle, we can use the thermal efficiency of the ideal Otto cycle, or thermal, or N Otto, or NTH, or N cycle. So let's use NTH, thermal efficiency. Okay? So we proceed with the solution. Um, so let's consider first, okay, step 2 to 3. So we want to know T3, ba? So let's consider step 2 to 3. And step 2 to 3, what type of process do we have? It's a constant volume process, right? Or isobaric. Therefore, in a closed process, in an isobaric process in a closed system, Q is equal to CV delta T. Okay, so from ChE 142, right? Therefore, okay, consider step 2 to 3. Okay, or constant volume, constant V process. Therefore, Q2 to 3, or QH, I mean Q in, okay, is just equal to CV delta T, which is T3 minus T2, right? And this is just equal to 800 kilojoules per kilogram, okay? So let's park that equation for now. Let's consider, kasi hindi pa natin alam yung uh, T3. Okay, hindi pa natin, yun yung hinahanap natin. Okay, so alam lang natin T1, and we also don't know T2. So, but we know CV, no? So, we want to know next T2, okay, so that we can use this equation to solve for T3. And how can we find T2? Let's consider step 1 to 2. So step 1 to 2 is an isentropic process. Okay, isentropic process, di ba? Ito siya sa TS diagram. What equation can we use in an isentropic process? Okay, so let's write first. Consider step 1 to 2, which is an isentropic process. Okay, isentropic. Um, so we can use the equation P1V1 raised to gamma is equal to P2V2 raised to gamma. Rearranging, okay, let's solve for P2, okay, let's solve for P2 by combining V1 and V2 kasi remember we're given the compression ratio, okay, P2 is equal to P1 times V1 over V2 raised to gamma, correct? So just rearrange the equation, and we know the value of P1, okay, we know the value P1, which is 100 kilopascals, okay, 100 kilopascals, and the compression ratio na 8, okay, V1 over V2, it raised to gamma, which is 1.4. Therefore, P2 is 1,838 kilopascals. Okay? So, how can we use this to solve okay, so in another equation, we can also actually use right, the temperature and volume counterpart. Okay. Okay. So we can also use T1, this equation T1 V1 raised to gamma minus 1. So remember, these are equations that we learned during uh, during ChE 142 equal to T2 V2 raised to gamma minus 1. And solving for T2 by rearranging the equation, it's simply T1 over V1 over V times V1 over V2 raised to gamma minus 1. Okay? And we know that our given T1 is 17 degrees Celsius, so it's 290 Kelvin, right? 290 Kelvin times 8 raised to 1 minus 1.4, which is zero point 0.4. T2 is 666.25 Kelvin. Okay. Now we can solve for T3 using equation, using the value for T2. Using this equation and substituting the known values. Okay. So for T3, 5 halves. So CV is 5 halves R, 8.314 joules per mole Kelvin. Okay. Times T3 minus T2, 666.25 Kelvin. Okay. Is equal to 800 kilojoules per kilogram. Okay. So, we want to convert this term into molar. Okay. So how do we do that? Use your dimensional analysis skills. 1 kilojoule is 1,000 joules times 1 kilogram is 1,000 grams. So times the molar mass of air, let's assume that it's 29 grams per mole. 29 grams per mole. Okay, so the unit will become joules per mole. So we're now consistent with the left hand terms. Canceling K and T3 is, so solving that equation, T3, you will get T3 equal to 7,000, so 1,782.44 Kelvin. And this is our T max as well. Okay. Next, we need to solve for P3. So easily we can we can use the ideal gas equation. Okay, so P2, V2. So for in ideal gas, diba, NR is constant, so we can equate P2 V2 over T2 equal to P3 V3 over T3. Okay, however, look at the diagram. V2 is just equal to V3. It's an isochoric process, therefore, we'll cancel on the on both sides. And we can isolate P3, and it's simply P2 times T3 over T2. Okay? Substituting the values of P2, which we obtained earlier. Okay? This one, P2, 1838 kilopascals. 1838 kilopascals multiplied by T3 over T2. 1782.44 Kelvin over 666.25 Kelvin. Cancel that. P3 is 4917 kilopascals. And this is equal to your Pmax. Okay, so now we're done for letter A. Our next goal is to find the work net. Okay, work net. So how can we find the work net? So remember, the work net is just Q in plus Q out. Okay, and Q out will have a negative value because it's the heat leaving the system. Okay. Um, so we have Q in, that's given. Q in is 800 kilojoules, but we don't have Q out. Right, Q out. So what do we know about the process where Q out happens? It's 0.4 to 1. It's an isochoric process. And therefore, if it's in a closed system and it's an isochoric process, diba, Q out is Q4 to 1, okay? And it's CV delta T. Okay, CV delta T. So it's CV T1 minus T4. Do we have all of the values here? We have CV and we have T1. We don't know T4. How can we know T4? T4. So we can utilize step 3 to 4 because we know already 3, T3, and P3. Can utilize this step to know T4. It's an isentropic process. Therefore, consider step 3 to 4. Three to 4, which is an isentropic process. We can make use of the equation T3 V3 raised to gamma equal to T4 V4 raised to gamma minus 1. I meant gamma minus 1. Rearranging the equation by isolating T4, this is simply V3, okay, T3 times V3 over V4 raised to gamma minus 1. Do we know V3 and V4? So far, we don't know V3 and V4. But V3 is simply equal to V2. This is an isochoric process. And V4 is simply equal to V1. And we know that ratio. Okay, we know that ratio, which is our um, compression ratio. So we can simply substitute equal to T3 times V2 over V1. Okay, because V3 equal to V2, V1, and V4 raised to gamma, and we know V2 over V1. So therefore, we can calculate T4, which is just substitute the known values, 44 Kelvin times, um, okay, V2 over V1, naman compression ratio V1 over V2. So, get the reciprocal of that. Kasi it's the reciprocal. 1 over 8 raised to gamma minus 1, which is 0.4. And this is equal to 775.85 Kelvin. Okay, so we now have T4. We can go back to this equation. Let's solve for Q out. Substitute CV. So CV is 5 halves R, 8.314 joules per mole Kelvin. Oops, what happened? Per mole Kelvin. Okay. Um, and then delta T, which is 290 Kelvin minus 775.85. And obviously, this one is higher than 290, so we are expecting that this term is a negative value. Okay. And then uh, multiply by the molar mass of air. 1 mole is 29 grams. 29 grams. So, ano yung magka-cancel? Cancel, cancel. Oops. So, it will, the unit is kilojoules, is joules per gram, which is obviously also kilojoules per kilogram. So, negative 348 kilojoules per kilogram. Okay, and now we can go back to our work equation, Q in plus Q out. Work net is simply Q in is given, which is 800. So minus plus negative 348. Okay, and this is 452 kilojoules per kilogram. All right. Next, we move on to letter C. The efficiency. Um, so we can make use of the equation of efficiency, which is work net over um over Q in, right? So we have work net na solve kanina and then Q in na 800 given. And this is 0.565 or 56.5%. Okay. We can also make use of the compression ratio equation. So let's try that. So what's our compression ratio equation for ideal Otto cycle? Diba ito yun? Raised to gamma. and then simply substitute everything, you will also get 0.565 or 56.5%. Okay? So now uh, we're able to solve all the required of the problem. Okay, there's also another way to solve the same problem. If we're given the ideal gas property of air table, so in the original solution, we assume that the specific heats are not a function of the temperature. However, if the problem would require that you consider the variations in the temperature or account for the variation of the specific heat with the temperature, and then they're given this property table for air, you can also use the property table. Basically, what you will do is go through the steps, just like how we solve the steam power plant problem. You go through the steps and identify the property um, at each step. Okay, so I will not show the solution. However, what you will get there is are values that are somehow different from our solution earlier. And the difference is because um, in the solution earlier, we assume the constant specific heat values. Okay, but for if we want to consider the variations in the specific heat with temperature, then it will give a slightly different answer. Let's proceed with the next problem. Okay. So here we're going to solve for a Brayton cycle problem. Let me go to the whiteboard. All right. A gas turbine power plant operating on a Brayton cycle has a pressure ratio of 8. The gas temperature is 300 kelvins at the compressor inlet and 1300 Kelvin at the turbine inlet. Utilizing the air standard assumptions and assuming a compressor efficiency of 80% and a turbine efficiency of 85%, determine the backwork ratio, the thermal efficiency, the turbine exit temperature of the gas turbine cycle. Okay, I also put here the TS diagram where the actual process, okay, is shown where there's an increase in the entropy in process 3 to 4 and 1 to 2. Okay. First, let's write the given values in the problem. Given, okay, given the pressure ratio, uh, and we designate that as RP equal to 8. So what again is the pressure ratio? Based on our PV diagram and PS diagram, diba? It's the ratio of P2 and P1. Based on our lecture, diba? It's the pressure ratio P2 over P1. And since this part right here for the Brayton cycle is an isobaric process, 2 to 3 and 1 to 4, it's also, the pressure ratio is also therefore equal to P3 over P4. Now, what else is given? Gas temperature is 300 Kelvin at the compressor inlet. So T1, and this is the compressor inlet, T1 equal to 300 Kelvin and T3, okay, what's 1300 Kelvin turbine inlet, T3. Okay, this is the turbine inlet, 1,300 kelvins. And then what else is given? Okay, let's assume that the efficiency of the compressor pa pala. Compressor efficiency, NC, let's label that as NC 0.8, 80%. And the turbine efficiency is 0.85. So what are the assumptions? Let's assume that um, air is an ideal gas. Okay, and uh, air is an ideal gas is Ig. Yeah, air is Ig. And also, we assume air standard conditions. So if air is an ideal gas, Cp is 7 halves R. Okay. Cv is 5 halves R. 5 halves R. And gamma is 1.4 for air. Alright. Then what is required from us? Letter A, the back work ratio. The back work ratio. Letter A and letter B, the thermal efficiency, end of the cycle of or NTH. So that's the same. And lastly, turbine exit temperature. So what's the turbine? Where is the turbine exit? T4. Okay. T4. So let's write that. Okay. Solution. What is the equation of backward ratio? Backward ratio, if you remember, in the Brayton cycle, part of the work of the turbine is used to drive the compressor. And therefore, backward ratio is the work of the compressor over the work of the turbine. Okay. And since we're given the efficiencies, okay, the turbine and the compressor, we're looking for the actual work. So let's label that convention as actual work, or simply you can just leave it as is because um we label the isentropic work as using the uh subscript S, but sige, let's label as actual. And then um do we know any of these values? Actually, both numerator and denominator we don't know. So let's solve for that. Work compressor actual. So let's begin with the efficiency equation of the compressor. So remember, it's the work, ano yung nasa taas when it's work requiring, but it's the, okay, work ideal. Okay, for a work requiring process, work ideal is in the numerator, it's smaller. Okay. So it's the work ideal or work isentropic over the work actual. So this is for the compressor. And this is equal to 0.8. Okay. So again, S for the ideal, A for the actual, S for the isentropic, okay, A for the actual or the real world work. Rearranging the equation, okay, we solve isolate work compressor. We isolate the denominator work compressor actual. That's what we need. Okay. this is a comma, it's simply work compressor ideal over 0.8. Okay. So how do we solve for work compressor ideal or the isentropic work? We can make use of, so we consider step 1 to 2. Consider step 1 to 2. Okay? What is step 1 to 2? So this is the compression step, right? Uh, I said PV diagram. This is the compression step in our process diagram 1 to 2. Um, so what we want to know is the actual work, but we can solve first the ideal work by since by assuming isentropic, right? By assuming isentropic and using the efficiency to solve the actual work. So if we assume that this is isentropic compression, what equation can we use? Okay, what equation can we use? Remember, for compression, uh, using the fundamental property relation, work is just Cp delta T. Okay, so it's Cp delta T. The compression, uh, work compression ideal is just Cp delta T. Okay, Cp delta T. So here, um, T is, we're referring to the ideal T. Okay, uh, on the diagram. Sige, so balikan natin. Okay, so we're referring to T2S. Okay, do we know these values? Also, kami mali. T1 should be T1. Okay, this one is T1. T2 minus T1. So this is 2, okay, minus T1. So do we know these values? No, but since this is an isentropic compression, so isentropic compression, we can make use of the equation T2 S minus T1. So simply we're referring to the ideal, okay, compression. P2 over P1 raised to gamma minus 1 over gamma. So again, uh, we learned these equations in ChE 1 for 2. Isolating T2S would give us T1, okay, just rewrite T1, okay, would give us this equation. All right, so do we know these values? Actually, yes, T1, we know it's given, and the compression ratio, P2 over P1. So simply substitute everything. I will not show it anymore. And raise to gamma minus 1 over gamma, you will get P2S equal to 543.43 Kelvin. Okay? Next. So the next thing to do is go back to this equation. Now that we have T2S and we know T1, we know Cp, we can solve for work compressor isentropic. Okay, work compressor. Oops. work compressor isentropic is simply 7 halves. Okay, 7 halves R, that's CP. So that's 8.314 joules per mole Kelvin times delta T, which is T2S 544.1 minus T1, which is given 300 Kelvin. Okay. And this would give us 7,083.69 joules per mole or kilojoules per kilomole. Okay. And then going back to the efficiency equation, divide this value by the efficiency 0.8, we will get work comp actual equal to 8854.61 kilojoules per kilomole. Alright, so we're done with the work actual of the compressor. We move on to the work actual of the turbine. Work actual of the turbine. So what again is the equation for the efficiency of the turbine? Diba? It's simply the work of the turbine, which one is the actual, which one is the isentropic. So for the turbine, our numerator, okay, would be the actual, it's smaller compared to the ideal. Okay. So therefore, the work turbine actual is 0.85 times the work turbine isentropic. Okay, so in my class, I usually designate yung isentropic as parenthesis S, but let's follow this convention for now. So how do we get work turbine isentropic? Consider step 3 to 4. Step 3 to 4, isentropic turbine. Isentropic expansion. Expansion. Okay. 3 to 4, 3 to 4, isentropic expansion. Okay, that's why it's important for us to be familiar with each cycle, uh, the type of the process for each type of the cycle. Okay. So again, since it's isentropic expansion, remember, we can use the following equation. Okay, work of the turbine is just Cp delta T. So this is the T4 S minus T3, where T4S is the temperature in the isentropic process. Okay, ito yun, T4S. So, so by the way, let me correct myself. Hindi pala fundamental property relation na derived to. It's the energy balance. So basically, work equal to delta H equal to Cp delta T. Okay? So sorry for that mistake. work equal to delta H isentropic, okay, equal to Cp delta T. And if you remember, since this is an isobaric process, delta H, so first nag-energy balance, work equal to delta H, okay? And then since isobaric process, delta H is just equal to Cp delta T, okay? So again, let's correct that. First energy balance, Cp equal to delta H isentropic, okay? And then because it's an isobaric process and we assume ideal conditions, this is equal to Cp T4s minus T3. Okay? So we can make use, since it's an isentropic expansion, we can make use of the equation T4s over T3 equal to P4 over P3 raised to gamma minus 1 over gamma. Okay, solving for T4, T4s is simply T3 over P4 over P3 gamma minus 1 over gamma. Substitute everything kasi we already know, we know everything. Tama ba? P4 and P2, yes, it's the compression ratio, the pressure ratio pala, pressure ratio, 'di ba? T3 is given. So substituting everything to this equation, we can know the value for T4s, and that is 717.66 Kelvin. Okay? Now we circle back to our equation for work isentropic Cp delta T. So just simply, so this is work turbine isentropic. Substitute Cp 8.314 Kelvin, delta T 717.66 minus 1300 Kelvin, and we will get a negative value because it's a work produced by the turbine or work done by the system, 16945. Okay, so let's make it 1645.57 and make it prettier. Okay, let's write that again. Kilojoules per kilomoles. And then going back to the efficiency equation, this is simply 0.85 times, so this is negative, negative 16945.57, and that would give us negative 14403.73 kilojoules per kilomoles. Therefore, our backwork ratio, which is the ratio of the actual compressor work and work required divided by the actual turbine work. So this is what we calculated earlier. divided by negative 14403.73, and then that's the absolute value. It's 0.62 or 62%. So that means that 62% of the work done by the turbine is used to drive the compressor for the Brayton cycle. So next we have B, the end of the cycle, N of the cycle, NPH, N cycle, or N Brayton. Okay. We directly make use of, say we assume air standard conditions. So make use of the equation here. So just substitute the values. This would give us 0.4448 0.448 or 44.8%. Okay, which means that out of the heat absorbed by the system, only 44.8% is um, used to do the network. Okay? Alright. Then lastly, letter C. Letter C, what is T4? Okay, what is T4? So we make use of the equation work turbine and is equal to delta H actual. But this is simply CP T4 actual minus T3. So we don't know the T4A, but we know the rest of the values, right? So because we know T work turbine actual, we calculated that earlier, negative 14403.73 kilojoules per kilomole, right? Okay, let's check. Okay, right. So there. So substituting everything and solving for T4, just simply get T4 actual, and that is 805 Kelvin and 0.01 Kelvin. Okay? Or is it 805 Kelvin lang? Anyway, please check. 805 Kelvin. So, teka, let's box the answers. I want a prettier box. Alright, so that ends our solution to the problem. And this is now the end of this video. Thank you very much.